Hello everyone, so today we're going to talk about the definite integral. So this is an extension of the Riemann sums we looked at last time. So let's recall what that idea was. So last section, we saw how to approximate the total change or basically area under a curve using rectangles to approximate. So we have some notation to start off with. So the definite integral uses a bit of notation, and it comes from really writing down the sum of all those rectangles in kind of a precise way and then applying a limit. So let's suppose f is a continuous function for so on some interval a less than or equal to t less than or equal to b. So the definite integral from a to b so it's written like this, where we have this elongated s with an a at the bottom, the start of our interval, and a b at top. And then we have f of t, and then we have that multiplied with a differential d of t. So what this is it's the limit of left or right hand sums of n subdivisions of the interval AB as t gets large. Okay, so essentially what's going on in the picture is we use delta x or delta t, whatever the input variable is, to describe the width of the interval. So there's two ways to see this. Basically, what we're doing here, actually, I wrote as t gets large, but it should be as n gets large. There's two ways to view the limit, as either as t getting smaller, n getting larger. So let me replace that. It should be as n gets large. So it's kind of like the same idea if you think about like pixels on your TV to get a sharper image. So let's say we had some small n trying to approximate a picture. You know, it might do an okay job, but say we have some a and b, and we just do a couple, like maybe three rectangles, left rectangles, let's say. We get some picture like this, and we're approximating our area using this picture. Now, there's quite a bit of room for inaccuracy with that picture, but as n gets larger, that area would be captured a lot more precisely. And that's the whole idea of this limit. So if we used a ton of rectangles, then they would be much smaller in width, and we would capture the area in a much more successful way. So, I mean, you know, we're not being precise, but you can just see as the rectangles are smaller, they're filling in the area in a much more precise way. And, you know, doing it by hand is not the best idea, but you definitely get the idea. As you increase the number of pixels on a TV, you get a much sharper picture. It's the same kind of idea there to the eye. when we had 480p TV, that's the number of pixels per square inch. That was, things, they probably looked good to us at the time, but once we saw 1080p, high definition come out, things looked a lot better. So that's the idea here. And we're not going to get too much into the nuts and bolts of applying the limit. That's more for a technical calculus course, not an applied calculus course. But let's just write it down to see exactly where this is coming from. So this integral from a to b of f of t dt, what this really is this is the limit as n goes to infinity of the sum of our partition from I equals 1 to n minus 1, where what are we doing? We're multiplying all of those function values at those particular endpoints on the interval, and we're multiplying by the width of our rectangles, which is given by delta t. You could that would be the left rectangle because we're starting at I equals 0. If we started one later, that would be the right rectangle, so that one would just start actually at, so I forgot the limit here, but it would start at I equals 1 and finish at n. So the right-hand limit would look like the limit as n goes to infinity of the sum of I equals 1 to n of f of ti delta t. Now, again, for any finite number of steps, those numbers are going to be different, but as you take the limit to infinity, they're going to converge to the same value. So before, what we'll do is we'll learn some actual techniques that will allow us to compute these limits for a lot of the classes of functions that we deal with in the course, namely polynomial, exponential, logarithmic, and functions of that ilk. Some rational functions also, and combinations of them via addition, multiplication, and composition. But let's just refresh how that process worked before we look at any of those examples. Again, we're looking for just kind of this big picture. How is this going to apply to our classes of functions? So this example is one we could have done perhaps last time, but let's just remember how it looks. So let's estimate, because we don't have any techniques of integration yet, from 0 to 12 of 1 over x plus 1 dx using a left-hand sum with n equals 3. So although it's the same type of problem, we do have to get used to the notation. So the thing to remember here is we really just want to find our, we're just using the technique from last time, but we need to find delta x. And how do we get that? Well, our interval is 0 to 12 from this notation, and we're using 3 rectangles. That's the value of n, so we do 12 minus 0 over 3. So that comes out to 4. And then we make our interval values. So we start at 0 and we count by 4s until we get to 12. 4, 8, 12. So there's extra length to this interval that we don't really need. But we're just doing the left-hand sum. So the left-hand sum approximation, the area, is going to be that width value of 4. And then we plug in each of the 3 leftmost points, 0, 4, and 8. So we're going to get 1 over 0 plus 1, plus 1 over 4 plus 1, plus 1 over 8 plus 1. And that comes out to 4 times the quantity 1 plus a fifth plus a ninth. And if you want to round that to 2 spots, that would come out to about 5.24. And that's it. So let's look at another example. Maybe we don't know the formula for a function. Maybe we have some, you remember from the very, very way back in the beginning of the course, we see functions are often represented not only with formulas, but also using tables of values and words and things like that. So what if we had a table of values? Let's try and estimate an integral using a table of values. Again, we're still going to be relying on our summation techniques for now, but we're still unpacking the notation since that's new to us. So use the table to estimate it's really just a compact way of writing the information. That's one way to think about it. But we're going from 0 to 15. Our function is f of x. We don't have a formula for it, but we do have some data points on a table. So let's say our function is given by this table where we're given these x values 0, 3, 6, 9, 12, and 15. And the y values are 50, 48, 44, 36, 24, and 8. So we want to estimate that integral, and we're going to use the table to do it. So let's recall all three of our techniques. Let's do the left-hand approximation, the right-hand approximation, and also the midpoint approximation. They don't tell us how many rectangles, but we can do it just based on the number of data values. We have 6 data values, which means we have 3 different ways of forming, well, we don't have the values in between, so we can't really do a midpoint, a true midpoint area approximation. We could sum them together. So let's do the left and the right and then figure out their average. So the left-hand approximation, the left-hand sum. Well, notice the x values are all 3 apart, so that will be acting as our width. And then if we're doing the left sum, we'd just be using the y values 50 plus 48 plus 44 plus 36 plus 24. And we get 606. And we see that this is a decreasing function. So for a decreasing function, our left-hand sum should be an overestimate of the true area. And for the right-hand sum should therefore be a under approximation of the true value. That's sometimes why it's a good idea to do both and then take their average. Again, the width is still 3, but now we're not starting at 50, but we're starting at 48 as our first point, and then using all the remaining ones, 48 plus 44 plus 36 plus 24 plus that last value, 8. And that comes to 480. So a good estimate for the area. So we could say the area, or the integral, from 0 to 15 of f of x dx is approximately the sum of 606 plus 480 over 2. I'm just taking the average of the left and the right. That's going to be a better approximation, and that's about 543. So again, we didn't use the formulas. We didn't have to plug anything into the function here. We just recovered the y values directly from the table. So for all of our examples so far, we've looked at things where the curve is above the x-axis. So how do the sign conventions come into play when we talk about these areas? Does it obey them in a normal way? So let's write that question down. What will the integral tell us if the curve is below the x-axis? On the interval. So how does that impact the value of that definite integral? So let's just think about what that would look like. Let's say we have some picture, and I don't know, maybe we're going from 1 to 3, and we have some function g of x that's looking something like this maybe. So if we look at an integral from 1 to 3, we'd be looking at this area. Notice this area is below the x-axis. So basically this corresponds to asking what is the sign of the integral from 1 to 3 of g of x dx. What is that value? So the answer there is it's going to be negative. So basically these integrals are behaving like signed areas. So as we traverse from left to right, if we're above the x-axis, that would be interpreted as a positive area, and below the x-axis as a negative area. So the integral is giving us what I call the signed area. of a curve. So from left to right, above the x-axis is going to correspond to positive. And below the x-axis is going to correspond to negative. So maybe we could do a quick example with just a picture. So let's say find the value of each definite integral by using the picture. So let's suppose our picture let's say basically we just have a picture that looks like this. So we call this f of x, and then maybe these x values, we call this one a, this one b, this one c, this one d, and then maybe we know the area of each of these. So let's say this thing has area 7, this one has, so this region right here has area 7, this region right here has area 3, and maybe this one right here has area 4. So we can ask a bunch of questions now. So let's suppose we want to do the integral from a to b of f of x dx. That's just the first region where it's pointing to the area being 7. A being at the bottom, B being at the top means we're going from left to right, and it is above the x-axis, so that's just going to be a normal value of 7. But let's say part B, we want to compute the area. Let's say we start at B and we go to C, and we're looking at f of x dx. Well, now that's looking at the area that's the second hump. So it tells us the area is 3. We're going from left to right, so that is going to correspond to, we're going to have to think of that as a negative area. So we're going to have negative 3 right there. So basically, if you're going from left to right, the first hump is going to be positive 7, the second one is going to be negative 3, and the last one's positive 4. What if we wanted to go over multiple sections? Well, what you can do is you can just kind of do them separately and sum them. So that's going to be a property of integrals that we'll write down more precisely later, but for now I think we can understand. If we go from a to d of f of x dx, we're basically doing the entire graph, all 3 shaded parts. So we would say, okay, well that's a 7 minus a 3 and then plus a 4. So this would have an area of 8, even though if you add the 3 areas together separately, 7 plus 3 plus 4 would be 14. The reason being is because 3 is below the x-axis, it's going to act as a negative area. If you wanted to get the true accounting of all the areas, thinking about everything as positive no matter what, there is a way to do that. And the way is we would not look at the area of the function, we would look at the area of the absolute value function. So let's say we did the area, the integral from a to d. Sorry, I wrote a b, I meant a d. But instead of looking at f of x, let's say we looked at the absolute value of f of x. Now that would be 7 plus 3 plus 4, which would come out to our value of 14 for the total area. Basically, the absolute value function takes all the y values and flips them over. It makes a symmetric reflection about the x-axis, because if you take the absolute value of f of x, it's always going to be a positive y value. Okay, so that's interesting. What if I throw in a couple more? So let's say part E. Let's look at that first section again, but what if we go from right to left instead of from left to right? What if we go backwards? So what does that mean? Well, that would mean B would be on bottom and A would be at top. So I'm starting at B and I'm traveling this direction. Okay, so that's how we would write it, the integral from B to A of f of x dx. And going from right to left adds one more negative sign because it's the opposite of the typical convention. So rather than this area being positive 7 now, it will actually be negative 7. And again, if you did the same thing to the second region, what would end up happening? Well, you would have a negative from it being below and then a negative from going the opposite direction. So how would I write that down? So let's go from B to C, but do it backwards. So C at the bottom, B at top, f of x dx, we would actually get the opposite of negative 3, and that would then come out to be positive 3. So that's how we can think of these definite integrals as signed signed values. So let's talk about antiderivative. So let's move on and do that, and then finally we'll make the connection. Basically, antiderivatives are going to be the things that allow us to find these areas for the classes of functions that we looked at exactly without having to use approximations using our Riemann sums. So let's write down the definition here. So given a continuous function, let's say little f of x, we say that capital F of x is an antiderivative of little f of x, provided when you take the derivative of capital F of x, you get exactly little f of x. So basically we're kind of thinking about the derivative in the reverse order. So let's try and think of a simple example and think about if we can find an antiderivative. So what is an antiderivative of, let's say, f of x, little f of x equals x squared? Well, we need to think of somebody that has derivative f of x, that has derivative x squared. Well, x squared is a polynomial function, and so we might expect that the antiderivative would also be a polynomial function. Well, why? The derivatives of polynomial functions are always polynomial functions, and they behave according to very regular rules, right? We just so let's recall the derivative rule for x to the n. So recall the derivative rule for x to the n. It looks like this. If you take the derivative, you bring down the exponent n, and you then lower the exponent of the monomial by 1. So the derivative of x to the n is n times x to the n minus 1. So if we have x squared, and we had somebody that was going to be its, so we looked at something that was going to be potentially an antiderivative. If derivatives, sorry, I was thinking in my head, I wrote down a 3. Well, that's exactly the point I'm trying to get at. If you have a function, a polynomial function that has an exponent of 2, and you wanted to say, well, who is going to have derivative that results in x squared, it would actually have to be 1 bigger, because the derivative rule is lowering the exponent by 1 each time. So we might think, okay, well, what is the antiderivative? Well, it's probably got to have a power that's a 3. But if you tried, so maybe your first guess would be something like f of x equals x cubed. But the problem is if you do f prime of x cubed, f prime of x, you would get 3x squared according to this rule. So this does not work. Because of the 3 in front. So we just have to adjust for that. So maybe our second guess, and we'll learn the rules for this and we won't have to guess every time, but it's good to try and think of on your own. So our second guess, we might say, okay, well, how would we adjust for that? If we know the 3 is going to come down and multiply, well, maybe we just say, okay, let's do a third of that value, 1/3 x cubed. And this works, right? F prime of x is then 3 times 1/3 x squared. The 3 and the 1/3 cancel, and we just get x squared. So this works. So then a follow-up question might be, is 1/3 x cubed the only antiderivative? Is that the only derivative of x squared? And so you might want to pause your videos and think about that. But fundamentally, the main part of it is going to stay the same. But there are things that have derivatives that equal 0 that would change it. So namely constants. So the answer is, in fact, no. The derivative of any constant is 0. Maybe say any constant function is 0. So adding such a constant would not make a difference. Right, so e.g., let's say 1/3 x cubed plus 12, or 1/3 x cubed minus 7, or even 1/3 x cubed plus pi are all antiderivatives of x squared. So we say if we write one-third x cubed plus c, where c is an arbitrary constant, this represents the quote-unquote family of antiderivatives of f of x equals x squared. So that's one example. There's lots of notation and lots of new names and things like that. But essentially, next time what we'll do is we'll look at antiderivatives. We'll write down the rules for polynomials, exponential functions, logarithms, and we'll learn the fundamental theorem of calculus that shows us how these antiderivatives are related to the general area problem we've been talking about. Technically, there's two parts of the fundamental theorem of calculus, so we'll only be looking at one of those parts, but it's the part applicable to finding these areas. So this is Dr. Lennon signing off. And I will see you next time when we talk about that.